go ahead and to do some research and some reading up as it pertains to latent heat of vaporization. I don't know how many of you guys went ahead and actually, read something about it, right? But as it pertains to that, this is kind of like the rundown as how you would basically find the latent heat of vaporization. As you know, vaporization has to do with a change of state from, liquid to gas. So one of the better ways to do it is obviously by starting out with a known mass of liquid. So if you're trying to find the latent heat of vaporization for water, you would start out with that body of water. You would need to know the initial mass, right? So initial mass, you can call it M1. So you need to know that mass. Now, as you can imagine, you're going to um, it's best if we set up this experiment on a scale, right? Because what you're going to see, you don't want to be moving around the thing whenever you're trying to take the measurements, right? So it's best to just set it up on the scale. So as you can see right here, we can take the reading of the water, and I mean, I think you guys should know by now that because you're measuring the mass of the water in a container, you would also need to know the mass of the container, right? One of the questions that we looked at recently involved something like this, where you would have to, well, not necessarily related to this, but let me see. So the mass of the container, right? You would need to know that mass as well. Now, obviously, when you add the water in it, that's going to be the mass of the container plus the water, right? So in a sense, to find the mass of the water, the initial mass of the water, then you would just subtract, right, the mass of the container from the mass of the water. So that's how you would find the initial mass, right? So our initial mass M1 is equal to the mass of the container, right, minus the mass of the container plus the mass of the water, right, minus the mass of the container. That's what we would do there. And obviously, you're going to start the experiment. It's an electrical method that we're using. So obviously, the energy, the energy obviously is going to equal to IV times the time, right? So the very moment you turn on the heater, you're going to start your timer at the same time, right? You're going to measure the voltage, measure the current, right? And when you're finished with the experiment, there are two things that we're going to do. Obviously, you would need to measure, you would stop the time at that point, and then you're going to measure mass 2, because what you would essentially see is that the water is going to get hot and, it's going to boil, and some amount of steam is going to be lost, meaning that water is converting from liquid to gas. And in that process, you can expect that the mass of the water is going to decrease. So instantly after you have stopped the timer, you would record the mass on the balance here. Obviously, that mass that you record would not be the exact mass of the water. It would be the mass of the container and the water. So you would then have to go back to find M2 by saying the mass of the container plus the remaining water. The remaining water, right, minus the mass of the container again, right? So that's how you would find M2. So we're literally doing a change in mass in order for us to be able to can go ahead and actually, find the overall specific latent heat of vaporization. So at the end of the day, this is what you would have. We know that the energy, right, required to, change the state of a liquid to gas is given by this equation, to say the mass of the liquid, right, times the latent heat of vaporization. By vaporization, right? So having said that, we are not completely there because this M is the change in M. So we have to then rewrite it as such to say Q is equal to M1 minus M2, right, times LF. Now Q is the energy. Q is equal to the energy. Let me see if I can write it somewhere else. I don't want to put it there. Let me see. So let's remember that Q is the energy, and that energy is, so Q is equal to the energy, but that energy is equal to I times V times T, and the whole reason for that is because we know that power is equal to energy over time, energy over time, over time. So if I want to find energy, I would transpose. So my energy is essentially equal to power times time, which is equal to M1 minus M2 times LF, right? Now, but remember now that power from an electrical standpoint is equal to V times I. So at the end of the day, we could just simply write our energy as I times V times T, right? Or we could even write it the other way around, but it doesn't matter, right? So this is the energy. So by way of just transposing the equation, we could see that LV, which is the latent heat of vaporization, is equal to pretty much your energy, which is IVT, divided by the change in the mass, which is M1 minus M2, right? So that is the entire scope of this this way of finding out the latent heat of vaporization. There are other methods, right? But this is a fair method to understand. Another method how we could have done it, you see, is by obviously boiling the water and then condensing back the steam, right, into liquid, right? And that mass of liquid that is gathered would be the change in mass. And so we could use that mass to pretty much find out what the latent heat of vaporization would have been. And if you check your textbook, you'll see that method in it as well. All right? Any comments, any questions as it pertains to this? All right, I guess not. Now, to just finish off this aspect of the content as it pertains to thermal properties, right? Another property that we can talk about whenever we're dealing with, liquids and so forth is evaporation, right? I mean, we have heard about the term evaporation, but do we really know how to explain it from a kinetic theory standpoint, right? We're going to look at that in this lesson here. I mean, anybody knows when evaporation takes place? I mean, the information is on the screen. You can look and tell me. But, if I mean, do you know when evaporation is taking place from when boiling is taking place? Let me know. How do you know when evaporation is taking place? And how do you know when boiling is really taking place?
Sir, with evaporation, exists before it would vaporize before it reaches its boiling point.
Hold on, bro, cause you I was using my computer audio. Let me just change something here. Hopefully it will work now. Say something. Let me see if I can hear you. As it pertains to the gradient from the graph, let's look back at my graph here. Right, I want to pick 2 points. I want to pick 2 points that could essentially, right, represent my gradient completely. So I'm going to pick it right here because this seems to be a point that I can easily recognize. And then, of course, which other one could I use now? So by way of just drawing my broken lines going across, I'm trying to find a point that I can read easily. And I think that is going to take me to this point. So when you're doing your gradient, try to get some values that you can read off of your graph. So I could see it now. So my x2, y2, my x1, my y1. Let's see what those values correspond to be. All right, so my x2 is going to be 300. It's going to be 300, comma, that no. Now remember when I was telling you guys about how you could find out what one of these small boxes represent? I'm going up by 5 degrees for every 2 centimeters. So if I'm going up by 5 degrees every 2 centimeters, yeah, go ahead. Yes, ma'am. No, but this point is not necessarily plotted. I'm going to show you that it's not plotted because it's from my line here. This number is going to be corresponding to this, not exactly this point. You see what I mean? So because this point is not underlined, then I wouldn't be basically using it. I'm just using probably the first value here of it, but it's going to correspond to something else. But I see where you're getting at. So in order for me to find out how much one of these small boxes right here to represent, I need to count how many small boxes are going up each time. That's going to be 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 small boxes in between my 5 centimeter scale. So for me to find out how much one box represents, I'm going to take my 5 degrees Celsius and divide it by 10. When I divide it by 10, I get 0.5. Let me just verify again. So 0.5, 0.5. So that is what one of the small box represents. So now, it means to say, if I want to find out this number right here, then all I need to do is to times 0.5 times 5, then I'm going to add that to 35. So when I do that, when I times this, I get 2.5 plus 35. So at the end of the day, my y2 point is going to be 37.5. That's how I go about doing this. If I can't easily identify what this line is, I'll go ahead and do the same thing for finding my x1 value. So what if I don't know what one of these boxes represent in between here? So all I would do is to say, all right, how much am I going up by? I'm going up by 60. If I'm going up by 60, it means that for every 2 centimeters, that is 60 seconds. So 60 seconds divided by the number of small boxes in between the 2 centimeter box, that is 10. So what it tells me that one of my boxes in between here, let me just verify. So one of my boxes in between there essentially represents 6. It represents 6. So if my point is located here, this is basically like my fifth box. Where is this thing? Come on. So this is my point right here. This is the fifth box basically that it is corresponding with. So I'm going to say 6 times 5 plus the number below it, which is 60. So I'm essentially saying 30 plus 60 is going to give me 90. So that is now going to be my x1 point. And then obviously I can easily find out that my y1 is going to be 20, 25. So having said all of this, I could go ahead now and easily calculate my gradient. The thing about your gradient, obviously, it's going to be y2 minus y1 divided by x2 minus x1. Now my y2 value is, my bad, 37.5 minus my y1, which is 25, divided by, 300 minus 90. So when I do all of this, right, let me work it out here. Let's see what time we have left now. Wow. Minus 25, I'm getting 12.5 divided by, 210. So when I'm finished here, I'm getting that my gradient is 0.0. Come on, thing. 0.059. Anybody got this? Somewhere there. Anybody got some of value such as close to this? All right, wonderful, wonderful. It all depends, Amanda. It all depends. I'm not sure how the graph looks, right? It could be based on the points. I'm not sure, but at the end of the day, yeah, man. You see, you'll be getting somewhere around that range. But you see, at the end of the day, you see, if we check your graph and we see, all right, you did everything correctly and all of that, and you got that value, and we can then, you can, you show the working out properly and everything, then we can't penalize it too much. But if there's something off, if the line is not completely a line of best fit, then that could explain why the gradient could be off, right? So having said this now, I want you to see something here, because this is what is going to assist us in the next part of the question. This gradient here, as you can see, y2 minus y1, that is basically your change in temperature divided by time, right? So that is what your gradient is, and obviously you can put a unit to this as well as, degrees per second for argument's sake. So to not run the risk of losing maybe a half mark, you can just put a unit right here. All right. So now we're going to take this information and we're going to bring it back over into this thing here. So my gradient here is equal to 0.059 per Celsius second, or Celsius per second, my bad. Now having said this, the question move on. And this question is sort of like related to finding the heat capacity of a metal. And if we remember that, right, we should remember that the equation would say that, um, Q is equal to the mass of the metal, right, times the specific heat capacity of the metal times the change in temperature, right? Yeah, man, that could work. That could work. That could work. That could work. So yeah, sometimes your gradient will be a little bit different. I mean, because it's subjective to you as a person as well, right? So, but at the end of the day, if you're getting close within that particular range, then it's fine, all right? But as it relates to Q, remember we said that Q is the energy. If we're dealing with the electrical method, energy is equal to I times V times T. I times V is what we call the power, right? So we could replace that to say that power times time is equal to the mass of the metal times the specific heat capacity of the metal, and I believe that's what we're trying to find, times the change in temperature. Okay. Now this is a tricky part because they asked us to use the gradient. So you initially would have to see that the gradient is equal to change in temperature over time. So you would have to then manipulate the equation so that you're seeing that. You want to use the gradient, so you have to bring that into play to say that my gradient was actually changing temperature over time. So what I will need to do, I'll need to divide this side by T, divide this side by T. So what we're left with now is that P is equal to the mass of the metal times the heat capacity of the metal times, no, this is now what we call the gradient, because that is now our gradient. So with all of this now, we can then go back and re-manipulate the equation to make C becomes the subject. So what you would be doing in essence is to say that gradient times T, which is the power. So if you read the question, it says that the heater provides thermal heat at a rate of 48 watts. So that's the power. So once you see watts, it's talking about power. Divide that now. Let me see if I'm doing the right thing here, Father. No, let me correct something here. Let me see if I did the right thing. Give me a second. So that gradient is multiplying on that side, so it would have to be dividing at the end of the day. So let's see here. So bring that across. It's going to divide. So P divide by the gradient, right? And then we're going to multiply that by the mass of the metal. That is now equal to the specific heat capacity of the metal. So let's see if we can get the answer now. So we have 48. We have 48. I realize my internet is a little bit unstable, right? We have 48 divided by the 0.0. Come on, thing, leave yourself. Right, so we have 48 divided by 0.059 multiplied by the mass, which is 1 kilogram. Let me hope that we get the answer by using that information. So yeah, at the end of the day, we're supposed to be getting that the specific heat capacity of the metal is 813.6, and obviously we know that is joules per kilogram per Celsius. So this is the answer related to this thing below here. All right? Are we all right? Yeah? Were we able to come to that consensus? Did anybody figure that part out? I know somebody had sent me some answer. I don't know. I don't remember if it was the same thing. Yes, Pat is well. Your one is a little bit higher. I don't know how. But either way, I think that answer could work. I don't remember what your specific heat capacity was, but maybe just because of the gradient, I should say. Maybe because the gradient was a little bit higher or lower, then it probably affected, so to speak. But this is essentially what would have been asked. You would have been tasked to do. Anybody, if everybody finished writing off, if they're writing off something here, all right. So Rihanna, somebody said Rihanna is saying her answer is that. I don't know if I made a mistake. Oh, and yeah, okay, okay, okay. I was just okay. All right. Either way, I mean, we can move on from there. Now, this question now comes over to this point because you see sometimes the questions are related. You pull one thing and it comes over here. So it says that the heater in part um, C is placed in some crushed ice, right, that has been placed in a funnel as shown. It says that the heater is switched on for 200 seconds and 32 grams of ice are found to be melted during this time. It says using this information, calculate a value for the specific latent heat of fusion for water. And it says state one assumption made. All right. So see if you can I know it's time is a little bit against us, right? But anybody can tell me what equation are we going to pull on here to essentially find out the answer? Anybody wish to share or wish to tell me? What kind of method would you call this method, by the way? What kind of method would this be? Yeah, essentially, but I get that, Patterson. But what is E? What is E? Tell me what is E? Yeah, yes, I know that. But what is it going to be in this regard? My first question was, what kind of method is it? What kind of method is this that we're using to find the latent heat of fusion? Remember, there are different methods. So clearly, we agree that the E is equal to mass of the ice, and this is a melted ice, by the way, right? Um, times the latent heat of fusion, right? What would be E? What is going to be E in this case? That's what I'm asking. I know that E is the energy, but what will it be? Yeah, yeah, Kerry, yeah, we can do work with that equation, of course. But I just want you to see something here. So I'm going to write what Kerry's sent just now. She sent that LF. She said that LF is equal to I times V times T divided by M1 minus M2. You see, the question gave us the overall change in mass already, so we don't have to necessarily worry about that part. So if you're only seeing only one mass value, that mass value is like the final mass that you would have needed. You understand? So yeah. So let's see now. Um, so having said that, so what I was trying to get at, guys, was that the energy E is really equal to I times V times T, where we said that the energy is really equal to the power times the time. The question said that we're using the same heater. If we're using the same heater, it means that it's going to have the same power. And they gave us the power already to say that P is equal to 48 watts. So what we're essentially going to do now is to just go ahead and replace IV as power times T divided by our change in mass. It's the electrical method, definitely electrical method, right? It's the electrical method. But the other method, I think the other method is the mixed method, and that one is probably a little bit more complicated, where it involves a long list of equations and all of that, right? So this one is somewhat more simplified. So all we go ahead and do now is to say, all right, power, which is 48, times the time, which is 200 seconds, because okay, so let me see here now. All right, so 48 times 200, we're getting 9600, divide that by 0.032. Yeah, so LF is going to be 300,000, and this is joules per kilogram, essentially. Yeah, thank you, guys. So as we go along, we could, since we know that P times T is joules, we could start writing our units in from that point so that you don't forget it at the end of the day, because it makes you look dumb. All right, it makes you look dumb when you're doing physics and you're leaving off your units. Okay, I know most of you guys don't want to be dumb. All right. Now, the next questions that are here. By the way, you were supposed to make an assumption. There's one assumption that we should make. Text in the group and let me know what one assumption that we could essentially, make right here. I want you guys, you see, to be very careful in terms of not paying attention to some of these experiments that we described, because if you check the narrative of some of the past paper questions, you will see that the past paper questions have it to say, describe a method of how you would find the specific heat capacity of something. Describe a method how you would, you know, use the calendar and calendar and Barnes continuous flow kind of thing. So we ought to be able to can actually, describe it in a sense, how you set it up, how you actually measure the things and so forth, right? And all of those things that we have been talking about, right? Don't neglect any procedures, right? Especially when we're looking at standing waves, when we're using the sound, the what do you call it? My bad. The tuning fork to find the antinode and all of that, right? Where the resonance occurring and all of those things. We ought to be able to kind of look back at it and see what is going on there. And I want to also tell you that whenever you're studying, my material is good material because it's concise, right? I would have looked, find out information that you would need to essentially, know to go into the exam. If you choose to decide to use a textbook and study, I can tell you that looking in that textbook is not ideal because it does not give you point to point things that you need to do. If you're going to use your textbook, you have to have your syllabus beside of you, comparing what you need to look at because there are obviously some crazy stuff in the textbook to just add more words into it and all of that. All right. So one assumption here is that it says that heat loss to the environment is negligible, indeed, right? So thank you, Patricia, for that. So essentially, that is what we're saying here as well. We could also say that the temperature of the floss, not the floss, but the funnel rather is negligible in terms of the temperature, or we could say assume that it's at zero, so that because if the temperature of the funnel is at a higher temperature, then that is going to add heat to the system, right? So those are some of the things that you could assume. You could assume also that none of the ice had started melting as yet, right? When you started the experiment. So those are some assumptions that we can think about. All right. So I'm going to give you guys this is an assignment, right, to do, right? I'm going to give you some questions pertaining to this as an assignment, um, right? But what I want to show you now that I'm going to show you where we're at in terms of the syllabus, right? And where we need to go afterwards so that you guys can see and understand what is taking place here, right? So this is your general syllabus. And you must have a syllabus, guys, right? So we would have essentially used or solved problems using these equations. Heat energy is equal to mc times the change in temperature, right? We use the one for latent heat of fusion, all of that coming down the line. We have explained cool. Well, I don't think I've explained cooling quite. I didn't talk much about cooling, but I talked about evaporation, right? So that is something that I could go back over cooling. You could do a little bit of reading up as to what is happening when cooling is taking place. We looked at, we discussed how specific latent heat um, of a fluid affects heat transfer between mixture. Maybe I need to find out what this is saying, but I'll get back to you on that one, right? But at the end of the day, we use both electrical methods. So it says that we should cover both electrical methods and the method of mixtures, right? And of course, it says use a calorimeter, which is more than likely a styrofoam to demonstrate it. We were supposed to do a practical pertaining to this, but obviously, that won't happen. We ought to be able to can explain the term specific latent heat, right? As it relates to the concept of melting and boiling, right? Changes in the internal potential energy. I would have stated stuff as it relates to that. So please ensure that you're going back over those things. So none of everything we are talking about, you shouldn't take it for granted. You understand? It says explain the concept of melting and boiling as it relates to no change in temperature. We went through that. That is talking about a change of state, right? We looked at the method of different methods that we essentially could use to find the specific heat capacity of a liquid or of a metal using the electrical method and the method of mixture. Here is where the calendar and Barnes continuous flow calorimeter comes into play. So that's the reason why I had to make mention of that, right? So it says that we should mention that the main advantage of using this in a sense right here. Um, so this is kind of like the more reliable thing to use, as I would have stated to you. Okay. So we have covered that. We have explained what is meant by heat capacity, right? And I told you that sometimes when you will have a substance that is made up of several materials, and it's hard if we want to, find the heat capacity or the specific capacity or then you would have to basically find the specific capacity of all of those substances that is inside of the thing and all of that. And to just eliminate that, we just decide to say, let's just talk about the heat capacity. That would just cover everything there and then, right? We spoke about a change in temperature as a rise in internal energy. We expressed the whole thing about internal energy in terms of having, being, sum of kinetic energy and potential energy. We talked about all of that, right? As we go back to this thing here, this is just going back further up to what we did already. We discussed the advantages and the disadvantages of the thermometers. So don't neglect those information. As I said, when you're studying, this is a guide that you have to use, the syllabus, to see if you're covering the actual points and all of those things. Now, this is where we're going to go next. We're going to go into what we call heat transfer, right? And that is going to essentially give us more information about what we call, conductors, you know, convection, because we know those are the main methods, and radiation. Those are the main methods of heat transfer. But this now is going to give us greater detailed information as to how we could find what we call a thing of what we call the temperature gradient, right, or the thermal conductivity of the material, all of those things. And there are also procedures, right? There are also procedures that we have to discuss. It says discuss or discussion on both the seals bar and the leaf disc. So those are some of the things that we have to speak to. We have to show you on all of those things. So we have quite a number of stuff to do, right? Speak about convection, understand what is happening with convection, thermal radiation. Then now in thermal radiation, we're going to talk about Stefan's equation, right? Where Stefan was able to essentially find out certain things that relate to black body radiation and all of that. Because what you have to understand, whenever radiation is occurring, it's basically electromagnetic radiation that is being given off, essentially light. So he was able to measure some stuff as it pertains to that, and you'll see it at some point. Then obviously we're going to look at climate change in this whole aspect and how conduction, convection, and radiation, works in different devices, right? Then from there we're going to go into the kinetic theory of gases, right? That's another realm of physics where you're now looking in greater details as it pertains to, and this is where it gets interesting, because we're going to do some proofs that are going to be mind blowing, right? But it's stuff that we have to know, stuff that we have to remember, and all of that. So all of these funny looking equations here, you're going to see the proof, and you're going to have to know how to come back to those proofs. Then we're going to move on to what we call, first law of thermodynamics, right? And from there, we then move on to the last part now. We're closer to the end. We can finish this in good time. It's just that we're going to be out of we're going to have exams, I think, for maybe 2 weeks or so. So my guess is that in order for us to finish up this, you have to sacrifice two class days in next week, meaning that Wednesday, right? We could use, as a matter of fact, we might Friday is Good Friday. So Wednesday and Thursday we have to have classes on those days, right? And I must say, we'll send out a message to the parents and all of that, so that you know that you have class, and the parents know that you have class, right? Because what you have to understand is that this is a trend from ever since, where we have to catch up. So we have to use the break as well to actually cover content. So it's nothing new. All right. So just be mindful of that. So we have to get through all of this thing right here. We can't lose. If we lose next week, dog, I'm gonna eat with supper, because by the time we come back to school, it's April 12th, right? And when you get back to school, you're gonna use 2 weeks out of that day, out of April, to do model exams. And during model exam, we can't really be doing teaching. So for us to can cover majority of what we need to cover, right? for us to be able to can cover. So we'll come back to school at 12. I don't know when the exams will start, but you know, just imagine that the exam is going to start the Monday for argument's sake. I don't know, or the other week, maybe the 19th. Then by the 30th exam will be finished. Then we'll have to get back. If we don't make use of some of the time in between here, then it's going to throw us off in May because remember the exam starts in June and we want to be able to can finish everything. You understand what I'm saying? Right? So we have to do that, guys. Yeah. We have to do it. As in, let me check when. Let me check something here as it pertains to the break. We're going off when? When are we going off? We're going off on Tuesday. All right. So here we're gonna have no. All right. Wednesday we can have class Wednesday. We're gonna leave out Holy Thursday. We're gonna leave out Good Friday. But chances are Monday morning, right? Monday morning and Tuesday, we have to have classes those 2 days. We have to have classes those 2 days in this week because, as we say, we have content. Remember, so you guys started late, so that is the reason why we're kind of running short on time. You guys started all the way down in November, so that kind of just make it a little bit difficult for us now as teachers. So we have to make up in that bracket. I know for a fact that I can use Wednesday to, because we're finished with something now, we're finished with what I went through a while ago, heat capacity and all of those things. We're done with that now. So I can use Wednesday evening thereabout an hour and a half to go through. Well, I can't promise that I'll go through everything for this part. Because this is, let me just check how many slides I have on this topic here. You see, this is a very long thing, This is 40 slides. This is 40 slides right here that we have to cover in terms of content. Maybe what I will do, I'll record the lessons too, because I think that can also work. I could record the lessons and disseminate it to you guys, and then I'll give you guys maybe a worksheet and so forth. Because I think we have to be creative when it comes down to that part. No, because as we say, time is against us per se, so we have to think proactive. Because this is 40 slides, and we're not done 40 slides in an hour, right? Because it's going to take time to break down the things, especially explaining all of what is happening here. And then now the next slide talking about kinetic theory would come next and all of that. So God bless you guys, and I'm going to send you guys this question. I'm going to send you the PowerPoint, so you just take the question out of it and answer it. All right? It's an assignment question.